Light, heat, charge, movement. All of these things are completely different, and yet we use a single term called energy to describe them all. Why is that? Why would they be connected at all? And most importantly, what even is energy? So first things first, what is energy? Well, energy is hard to define, but we all have a pretty good feel for what it is. So for now we can say that it's just the capacity for doing work and a conserved quantity. So if we had a ball, for example, moving forward and hits another ball, all of this energy will get transferred. That's kinetic energy, and it basically means movement times mass. Since energy is conserved, there isn't actually a way for us to lose this energy, and that's why it got transferred when our balls hit, because energy can't just disappear. Another kind of energy is potential. So if we take our ball again and move it up this time, the gravity wants to pull it down. We call it potential because there isn't really any physical representation for it. I mean, the ball isn't heavier, isn't glowing, isn't moving faster or at all, in fact, it's just there, chilling. But if we let it go, it falls. That's potential energy. It doesn't always have to be height. Potential just means potential to release energy. If you were to graph the amount of kinetic energy our ball has, you would see that it's disappearing. And then when we release the ball, the energy is reappearing. But this doesn't actually track with our definition, since we said energy can neither be created nor destroyed. It's a conserved quantity. So that's why we made up potential energy. We just say that instead of our kinetic energy disappearing and reappearing, it's getting converted into potential energy. So if we add another line, summing both energies together, it will always stay constant, which means that the more energy we in quotes lose right here, the more we'll gain right here. So the lower this drops, the higher this gets. And so let's just recap for a second. This red line right here represents our kinetic energy, so the movement of the mass of the ball. Kind of like velocity. Actually, in this case it will be proportional to velocity. And the blue line represents the potential energy. In this case, the energy that can be released by gravity, so the height. Got it? Red line is the velocity, blue line is the height. I'll let this animation go in the background for a second. Now both of them summed up give us the total energy, which is always constant. Except it isn't, and based on what I described, it really seems weird. I mean, in what possible scenario would this line not be constant? No, really, this is a genuine question. Pause for a second and see if you can answer it. There. Got it? Well, the answer is pretty simple. And the animation was a bit of a hint in itself, because at the end of it, our ball is stationary and on the floor, which means that both its kinetic and potential energy is zero. So our total energy of the ball is also zero. So what happened to the energy? Well, it got transferred to the ground, and that's where we find the actual constantness of our energy, and that is the total energy of our system, the green line, which would be the energy of the ball plus the energy of the ground, so this. This is the line which will always be constant, and that's why sometimes you'll hear insulated system in physics. What insulated system basically means is a system in which the total energy stays constant. But hold on, I just said that the ground here has some energy, but what kind of energy? It's certainly not kinetic, since it's not moving, and obviously not gravitational potential, since there is no place for it to fall. It's the ground, it's on the ground, so what energy did this ball movement turn to? Well, this energy turned into thermal energy. What is thermal energy? Well, thermal energy is just the average movement of molecules. Now to that you might say, hold on now MAKiT, wouldn't that just be kinetic energy? I mean, it sure seems like if we move one of the molecules, it's kinetic energy. So when we move all of them, shouldn't it also be kinetic? And the answer is yes. Yes it is. We just differentiate between them because it's a bit useful, but temperature is just the average movement at molecular scale. We'll get to why it's different than kinetic soon, but let's leave that for later. Next kind of energy is radiant. Radiant means electromagnetic waves, so light. When it comes to light, it's different. So far, both kinetic and thermal energy just mean the movement of stuff, so mass times velocity times velocity. But with light, it's different. Its velocity is constant, so c, and it has no mass. So what is its energy equal to? And that is a phenomenal question with actually a rather simple answer. You see, okay, so basically, photons, so light, are kind of a particle and kind of a wave. So the energy would actually be proportional to its wavelength. That's where we get the light spectrum from, and something not many people realize about the light spectrum is that it's measured in meters, so its wavelength is really just the length of a wave. It's just length. Which means that wavelength of 10 picometers would be gamma rays, wavelength of 100 meters would be radio waves. So the longer the wavelength, the lower the energy. So this photon has a lot of energy, and this one, not a lot. That's radiant energy, but photons aren't the only elementary particles that can act as energy carriers. There's also electric, so electrons, and with electrons, it's the exact same thing as kinetic. Again, just movement of something, in this case, electrons. But with electricity, it's a bit different, because all those electrons are negatively charged, so they repel each other, which is different from standard matter, which comes together due to gravity, but that's kind of it. And I've already made too many videos about electricity and electrons, so let's move on to the last one, which is chemical energy, which basically just means the bond, so carbon dioxide, for example. Carbon dioxide molecule has a single carbon atom and 2 oxygen atoms bonded together, but what is keeping them bonded together? What force is holding them close and not allowing them to drift? Well, this is a bit counterintuitive because there is no force actually keeping them together. Instead, you need energy to break them apart. Imagine like this, you have a ball floating in space. Here I'll just add an axis for reference. Now if someone were to ask you a question, what is keeping this ball in place, how would you answer? Well, you probably say nothing, because there really isn't anything holding it in place. Instead, you need force to move it. And that's what's happening with our bonded atoms. There is nothing really holding them together. It's just that you need energy to break them apart. And with that explanation, we can finally get to switching energy, like electrolysis, so turning electrical energy to chemical energy. And this one is pretty simple, that's just water. Or rather, what we can do with water. You see, water is made of 1 oxygen and 2 hydrogens, bonded like this. Now, what is the reason for the bond? Well, molecular orbital theory. Okay, it sounds awful, but you have to trust me, it's way simpler and more useful than it seems. Let's start simple with how we divide electrons. We divide them into shells and subshells. We do it for some boring quantum mechanical reasons, which we won't really get into right now because they are irrelevant. But here are the 2 most important things. First of all, energy. Hey, that's what this video is about. Here you can see these shells and subshells ordered by their energy. So the higher the electron is, the higher its energy. And because, as I mentioned, things don't really like having energy, electrons start filling these shells from the bottom up. Then the next thing is orbitals. So how many electrons can we fit on each rectangle? Well, we can divide those rectangles into squares which are called orbitals, and each one can fit only 2 electrons. There. Orbital theory. Now to add the molecular with water. So why are atoms in water together? Well, it's because when 2 orbitals come together to form a bond, what they actually do is they form 2 new orbitals. The bonding orbital and the anti-bonding orbital, because of some quantum mechanical mathy function magic, which I explained in another video. Now the whole idea looks like this. The bonding orbital has less energy, and the anti-bonding orbital has more. When our hydrogen and oxygen bond together, their electrons move down from their orbitals to their bonding orbitals, releasing this difference in energy in the process, and they stay bonded. In order to break the bonding, you need to pull these electrons back to their original orbitals, which means bringing energy in. That's why if we have water, for example, and we'd like to turn it to hydrogen and oxygen, we need to bring in additional energy. So first what we do is we pull these electrons out, destabilizing the bond between hydrogen and oxygen and keeping them separate. Now, once the bond between two oxygens is high, it's still lower than oxygens being by themselves, so they bond to reduce their energy as much as possible. Now what we do is we introduce these 4 electrons back, allowing the hydrogens to bond into a gas. Now that we have this higher energy hydrogen, we can turn it back into water to release this energy in the form of fire. Or in other words, we can turn electrical energy, movement of electrons, into chemical energy, unstable bonds, which we can then turn to kinetic energy, explosion and thermal. So there, we can easily switch between different energies, and these energies cannot be destroyed nor created. Except there is a problem, because you see, if we draw a full diagram for this, we can see that we can use the explosion to power a generator to move the electrons, and then the cycle is fully complete. If not for the loss of energy. Loss of energy? I thought energy couldn't be destroyed nor created. And yeah, it can't. But the energy lost isn't really a loss of energy. It's energy lost as temperature. Machinery gets hot and the thermal energy leaks away. But why would we consider thermal energy as lost? Well, it's because temperature is the ash of energy. And here's where we introduce entropy. So what is entropy? Well, entropy tells us how much useless energy is there. Okay, that's cool, but what is useless energy? Well, imagine a hot cube, like really hot, scalding hot. Then imagine placing an engine on top of it, which turns heat into electricity. Now, after placing this engine, we get electricity and we can use it to do work. In this case, I don't mean the human abstract kind of work, I mean the physical unit of work. Now, what's really interesting is that for thermal energy, when we use it in engines, we don't really actually care about how hot something is, only about how hot it is in relation to other things, like the engine, for example. Now, why is that important? Because of entropy. We really often like to think of entropy as mixing stuff together, and there is a reason for it. It's because when you mix stuff together, it takes less energy to mix stuff than it takes to pull them apart. But the energy stays constant, which means that it takes less useful energy to mix than to pull them apart. And whilst energy is the theoretical measure of work you can do, entropy tells you the difference between the practical amount of work you can do and the theoretical one. So going back to our thermoelectric generator for a second, so the generator which turns thermal energy into electrical energy, there is a problem. Because you see, this generator doesn't really need thermal energy. What it needs is a difference in temperature, so a difference in thermal energies. Which means that if our generator was just as hot as the cube it sits on, it would generate no electrical energy. Even though both the generator and the cube are extremely hot, so they have a lot of thermal energy. Because of entropy, there's just no way to convert it into anything useful. That's why sometimes a system with more energy but less entropy can be preferable to one with more energy. Because there is just more useful work to be done. And that's why heat is the ash of energy. It's because when it comes to temperature, the energy is distributed so evenly that there's just no way to use it. That's why we differentiate between them. It's because whilst both thermal and kinetic energies describe movement, this movement is much easier to use than this movement. Hence, this is useful, and this, most of the time, is just a loss. And that's all fine and well in theory, but what's the actual practical difference between kinetic and thermal? So let's start with force. I won't overcomplicate it too much. If you have an object with mass m and you push it, then the stronger you push it, the more it accelerates. You can describe the strength of a push as F, and that's the force, well known as the equation of F is equal to ma. In order to truly understand what this means, let's break it down a bit. What is acceleration truly? Well, acceleration is just change in velocity in relation to time. What is velocity? Well, velocity is just change in position in relation to time. What is position? We're not doing this bit. No, I'm not. We don't have to do this bit because position can be described with base SI unit, a meter, which means that we can describe velocity as meters per second, and acceleration as meters per second. Now to this we add mass, which also has a base SI unit of kilograms, and there. Now we can describe the force in relation to just base SI units. And what I like to do now is something that most physics teachers skip. A step which is incredibly important to cement the understanding of complex equations, but really often overlooked. And that's asking the question of, does that make sense? In order to understand that, we have to imagine two cubes, first one bumping into the other one. Both of these cubes have their own mass. This cube is traveling at a certain velocity, so it has some sort of momentum. Irrelevant. Now when it hits this cube, it accelerates. And that's where our equation comes in handy. It basically says that the higher the force, the quicker it accelerates. So the more meters it can cover while accelerating, the shorter the time for a certain acceleration to occur, and the bigger the mass it can accelerate. That's why all the units are there. Now we understand force, we can get to work. On understanding work. So what is work? Well, work can be defined as distance we push this cube over. Okay, well, it's not quite the distance itself, it's like the amount of distance the force acted on, so like how far we pushed. So force multiplied by distance, that's work. So how far we pushed, but pushing is like an essential part. It's force times distance. So imagine a MAKiT intern pushing a cube. This MAKiT intern is actively working, which means that the work being done is equal to the force of the intern pushing multiplied by the distance the intern is covering. But how does that relate to energy? Well, energy is the capacity for work, which means that in this case, this is the equation for energy. Kinetic energy of this cube. Now this example is a bit tricky because we have our MAKiT and then pumping new kinetic energy into our system by pushing the cube. And the cube is losing the energy as thermal energy because of friction, but that's the equation for kinetic energy of the cube. So the work it's doing. Now it's time for the electrical energy equation. And so for electrical energy, we're talking about electrons and their movement. So for electrical energy, we're going to start with this. I won't re-explain how to get this equation here because that's a story for another time and another video, so for now you'll just have to trust me with this equation. Equation which says that the velocity of our electrons is equal to the charge multiplied by the magnitude of the electric field per mass times time. Okay, the point is if we divide both sides by time, we'll get acceleration equal to this. And if we multiply both sides by mass, we'll get force equal to this. I think you can see where this is going. Back in classical mechanics, we took the force acting upon an object, multiplied by distance, and got the work done. We can do the same thing here, so we can multiply it by the distance and turn this magnitude electric field into voltage. Now we get the energy equal to voltage times charge. What does that mean? Well, imagine a magnet. What this equation says is that the stronger the charge of the magnet, or the stronger the potential acting on it, the more electrical energy it has. That's what happens in our cables, except instead of a magnet we have electrons, so that's electrical energy, not quite magnetism, all the kind of words. The point is, that's electrical energy. Next we'd have... Alright, remember what I said about the radiant energy being related to the wavelength? Why is that? Well, let's go back once again to kinetic energy and its equation of ms squared divided by t squared. Now we can break this equation down into ms divided by t, s divided by t, and we can group those two into E is equal to pv, which means that our kinetic energy is just equal to momentum times velocity. Now for electromagnetic radiation, it's a bit tricky, and that's because our velocity is constant. It's the speed of light. So our equation becomes E equals pc. And because of some really difficult to understand relativity / quantum physics, which I just gave up on understanding on the stream and just left it for the wave map video, momentum of photons is just equal to this, where h is the Planck's constant and lambda is the wavelength of the photon. Next up we'll have, for thermodynamics, it's really similar to kinetic energy, except this time it's more average. So how could we get that energy? Well, once again, for the fourth time, let's start with E equals ms squared divided by t squared. Now it's time for the ideal gas law equation. So this, PV is equal to NKT, which states that the pressure times volume is equal to the number of particles times the Boltzmann constant times absolute temperature. Now, in order to analyze why this equation could be useful to thermal energy, let's start with the right side: amount of molecules, Boltzmann constant, and absolute temperature. In this case, we can just omit the Boltzmann constant because it's not really important. What is important is the N times T, because the absolute temperature basically tells us the average kinetic energy of a particle, and since the N tells us the amount of particles, there. Now let's go back to our E equals m squared T squared and define another unit called a Pascal, which is just force per area, which is just P is equal to m1 divided by T squared S. Now we can see that if we take this pressure and multiply it by length, and again by length, and again by length, we get this. So P S cubed is equal to m S squared divided by T squared. Or in other words, PS cubed is equal to the energy. And what is length times length times length? Well, that's a volume, which means PV is equal to E. And if we merge it with the ideal gas law equation, there. So that's the thermal energy. Well, one of them at least. And right here we can already see a certain pattern develop. You see, first we started with classical mechanics and this equation. Then for electrical energy, we took this equation and modified it to account for charge with this equation. For radiant energy, we did the same thing except with this equation to account for the lack of mass. For thermal, it's once again the same thing except with this equation to account for the statistical nature of thermodynamics, and there is a reason for it. You see, this equation just tells us the capacity for work in normal everyday objects like balls or cubes or whatnot. But in the realm of photons or charge or average movement, this isn't enough, because this is only true for the classical model of physics. That's the thing. If you think about it, work is just a concept. That's it, nothing more. We made up the concept of work to describe different behaviors of different things. Then we made up the concept of energy to describe how much work something can do. But we can't really simulate all of the atoms in a cube of iron, and the intricate behaviors of the electron clouds, elementary particles, intramolecular forces, intermolecular forces, and so on. And that's why we invent models to simplify things. Of course, nothing is free, so a classical model may be simpler than simulating everything, but it's less accurate for classical objects. And if you apply it to something like photons, it breaks down completely. There is no mass. That's why we need to modify it for photons. So that would be the point of this video. Energy is just a concept. Like anything else in physics, different kinds of energy may be treated differently, but they are just capacity to do work. And there is no better example than... So what is potential energy? Well, if we take a look at kinetic energy, we'll find a pretty straightforward explanation. In physics, the kinetic energy of an object is the form of energy that it possesses due to its motion. Simple as it could be. Then we have this equation as a sort of general equation describing it, which we can modify it for different cases. But then we have potential energy with definition like this. In physics, potential energy is the energy held by an object because of its position relative to other objects, stresses within itself, its electric charge, or other factors. Other factors. That's so vague. What other factors? What kinds of factors? Gravity, charge, quantum, nonsense? Well, all of them. For kinetic energy, we not only have a concrete rigid definition, but also a general equation. But for potential energy, we have this. A function. What is this function equal to? We don't know. In order to describe it fully, you'd have to account for every single thing in this universe which might give you some capacity to do work. Physicists do differentiate between kinetic and potential energy, and there is a solid line between them, but that's only because potential energy is a bit of a misnomer. In reality, it should be kinetic energy for all movement and static energy for everything else. That's because all energy is potential energy. All energy is just potential to do work. All of the things I've described so far and more, like gravity and chemical energy, aren't connected by a solid line. They just all influence each other. That's what existence is, affecting something, leaving an impact. Light, heat, charge, movement. All of these things are completely different, and yet we use a single term called energy to describe them all. But that's it, to describe them. with different models, different equations. We're trying to describe these completely different forces into a single coherent science. And that's what physics is. Physics is the answer to a question of what is energy. And so that's the video. I really hope you enjoyed this video about energy, a bit of physics. And fun fact actually about this video, yeah, this is the ad segment. This is the MAKiT is having a mental breakdown part of the video, and that's because I stream every single day. Right here you can see on screen all the thumbnails for these streams. And so fun fact, this entire video actually has been made on streams. Yeah, multiple, because it actually took weeks to make. Literal weeks. All of the live streams from me making this video are on YouTube, and if I sound a bit off now, that's because this is actually the ending of the final live stream. We're currently 5 hours in. There's still a couple of animations left to finish. So if you'd like to join me on any of these live streams, then go ahead and join. I stream literally every single day. Also, I have a Patreon in case you'd like to support me. A couple of tiers, fun tiers. Like, for example, you get to decide what the new Make in the Corner should look like. And Discord. So I have a Discord server in case you'd like to join. Anyhow, subscribe, like, and I suppose that'll be it. Thank you everyone so much for watching, and have a great day. Bye.